Hi, thanks for joining me today. I've got a fun, quick number theory problem to show you. Okay, so we have a and b natural numbers with a and b coprime. And we want to prove that there exist other natural numbers m and n, such that a to the m plus b to the n is congruent to 1 mod ab. So mod a times b. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself. And I'm going to jump straight into a solution. Okay, so to solve this problem, I'm going to be using the Fermat-Euler theorem. I'm just going to state it in this video and I won't prove it, but it's quite a common number theory result, a very standard result as well. Okay, so the theorem says that if we have c and r natural numbers, which are coprime, then c to the phi r is congruent to 1 mod r. Now, this phi r here is the Euler-Totient function, so it takes in a natural number, and in this case r, and it spits out the number of numbers less than r, which are coprime to r. Okay, so if you consider the set, so phi of r is precisely the cardinality of the set of S for which S is less than r, and GCD of S and r is 1. Okay, so it's a set, so we look at the natural numbers S less than r, which are coprime to r, and we take the cardinality, so the number of elements less than r, which are coprime to r, that's precisely phi of r. Okay, and the Fermat-Euler theorem says that c to the phi r is congruent to 1 mod r. Okay, again, I'm not going to prove it in this video, I'm just going to state it. But now what we're going to do is choose m to be phi of b and n to be phi of a, and then I'm going to show that then a to the m plus b to the n is congruent to 1 mod ab. Okay, so by the Fermat-Euler theorem, plugging in, if we look at a to the m, that's going to be congruent to 1 mod b, because remember a and b are coprime, and then so m is just phi of b, so a to the phi of b is congruent to 1, and that's simply by the Fermat-Euler theorem. And similarly, we have that b to the n is congruent to 1 mod a. Okay, let me bring these two up to the top of the whiteboard, and we'll continue. Okay, so we have that a to the m is congruent to 1 mod b, and b to the n is congruent to 1 mod a. But in particular, this means that a to the m minus 1 is congruent to 0 mod b. Okay, but also notice that b to the n is going to be congruent to 0 mod b, because of course b to the n is clearly a multiple of b. So if I add b to the n on this thing here, I also get that b to the n plus a to the m minus 1 is congruent to 0 mod b. And similarly, b to the n is congruent to 1 mod a, so that means that b to the n minus 1 is congruent to 0 mod a, but then I can add a to the m to both sides, so I get that b to the n plus a to the m minus 1 is congruent to 0, this time mod a. Okay, and now what I can do is, because a and b are coprime, I can sort of combine these results here and conclude that a to the m plus b to the n minus 1 is congruent to 0, and then I multiply the two together, so mod ab, and now we're done, or well, we just add 1 to both sides, so we get that a to the m plus b to the n is congruent to 1 mod ab. Okay, and now we're done. We've found m and n, and we've actually found them explicitly. M is phi of b and n is phi of a, and then we've shown that a to the m plus b to the n is congruent to 1 mod ab. Okay, a nice quick video for you today involving number theory. If you've not seen the Fermat-Euler theorem, I encourage you to look it up and look up the proof. But yeah, that's all for today's video. I will catch you in the next one. Have a great day.